I had there was a physics lecture. He held this, it was this big, one of these big rooms, 200 there. You would come in and yell at the top of your voice, sit down, shut up. This was just down the hall from me. It was always, I knew what time it was. So Dave Boyle was going to start class.
Was this recently or just past?
Yeah, he's not with us anymore. Okay, so we're just beginning to understand the Schrodinger equation. And you can see that obviously there's a new kind of physics involved in this, and the guys are just groping, trying to find some way of doing this empiriometrically in some way to gain some understanding. You can see how the empiriometric is a tool when properly used to gain insights into things that are extended beyond our senses. We have to be careful about understanding. And so Schrodinger is looking for a wave equation. He thinks that the electron has both, the experiments involving electrons are demonstrating that there are two entities involved, there's a particle and a wave. And so there has to be some kind of equation which will reflect the wave nature that's present and also the particle nature. And so he writes this wave equation down, which we started discussing last time. It involves some wave function, psi of x and t. And initially, he's looking only at the kinetic energy. So for a free particle, then this gives the proper dispersion relation that we were talking about before, namely the relationship between the frequency and the wave number that corresponds to a particle with mass m. So this gives rise to this relation. If you substitute in an exponential function, e to the I kx minus omega t, so this comes out, this relationship, the left hand, right hand side, you cancel out the psi. Okay. So, but the free particle is not really very interesting. We're interested in what happens when the electron, for example, is in the neighborhood of a proton and is attracted to the proton. Or something else, some other kind of way of confining an electron. And so he's extended the free particle to include now, if this is interpreted as relating somehow to the kinetic energy, then we would add potential energy as a function of x in one dimension. Could be then when we go to the hydrogen atom, we'll have potential energy for the electrostatic interaction. So it's the product of the charge divided by the distance. Negative, subtract. Okay, now the solution is different. It can't be what we just wrote down. Not simply a plain width. So he's written down this equation. He still doesn't know what is this thing. He's anticipating from work in other wave equations that he's going to get some kind of quantization condition. The solutions to this equation will be quantized for discrete energy levels. So he's expecting this, for example, looking at a drum head, where we could write down the wave equation for the membrane and require that the amplitude of vibration vanishes on the outside, on the edge of the drum head. Then we can look at the solution to the wave equation, get frequencies corresponding to different modes of vibration. He's very familiar with this. Most physicists would be at the time. So the frequency spectrum of the drum head, there is not just a continuous range of frequencies, there are discrete modes. That is, there are frequencies that are corresponding to different vibrations. So for example, let's take a drum head like this, and we can have a mode where the drum head is going up and down like that, flexing in and out. I'm going to draw it like that, which means that it comes up, everything is up, or then it flexes down. So that would have the base frequency, that would be the lowest frequency of the drum head. You could also, if you're good at it, excite the drum head in another mode of vibration, which would be up here and down here with a node in between. Remember the standing wave that we drew earlier had nodes. You can extend this to two-dimensional systems like this, where there would be a node here. So the drum head is doing this with a node along the line between. This would have a higher frequency. And there would be a discrete, there's a separation between these frequencies. There would be other modes with the same kind of structure, but this is an independent, this mode is independent of this, meaning that you could excite them independently of each other. And so I can keep drawing more such modes and anticipate how this might go. And notice what I'm drawing in here are the nodes. So, oh, yeah, just bring it right. Do this one. Oh, there you go. Okay, so here's another normal mode, these are called. Where we have these quadrants are coming up, and these two quadrants are going down, and these things just fluctuate like this, oscillate like this, and the frequency is going up. From here, these are the same frequency. This is another mode, a higher frequency. He's expecting something like that. That's what's motivating this, writing down the wave equation. He's expecting that there's going to be some kind of discrete solutions for like the hydrogen atom. And is this going to correspond to what is seen in the hydrogen spectrum? So that's what's going on in this one. This was not the first equation he tried. There was another Schrodinger equation before this one, which failed. And it had very good reasons for writing down the equation that he tried. And the reason for the failure was unclear to him at the time. It turned out later that the first Schrodinger's equation was reinvestigated later. And it was found to, the reason for the failure had to do with the fact that it was the solutions to the equation corresponded to particles and antiparticles. Antiparticles were not known at the time. So Schrodinger didn't recognize what was going wrong. It was actually a feature. It wasn't a bug. It's actually something real in the sense of being that there's a real prediction of the theory. So Schrodinger's first equation contained too much. He didn't understand how to work it. Wasn't able to give solutions. And this was actually his second. So he was actually discovering more than he could handle at the time. It wasn't until Dirac wrote down a different equation. So there are several equations in quantum mechanics that are wave equations. Another one is the Dirac equation, which is actually a better description of the electron than this. So what this doesn't have in it is an aspect of an electron. An electron is really pretty simple. It's got mass. Can change place, right? So it's got impetus. It has charge, electrical charge. It also has a weak charge, which means it's interacting through a different force than electric field, a weak field. Very short range interaction. It has a weak charge. It's also got a thing called spin, which is an internal angular momentum. And that's not present in this equation, but it's present in the Dirac equation. So all of this progression is taking place within a short time, within a couple of decades. Huge advances are suddenly opened up. And as I said, this is really where things start to cook. His first attempt did not work, not because it didn't work, but because he didn't understand. Then things, when he gets to the solution of this, as we shall see, I'll show you here in this class, we'll go through this. Write this down for the hydrogen atom, and we'll see, bango, there it is, the spectrum of the hydrogen atom comes out. This was what people were really looking for, is to have some understanding, but they still don't know what this is. What is this thing here? It's not like, remember we derived the wave equation for a string, or a piano wire under tension, and it's the deflection of the wire from the string. And then I told you, well, you have a rod of some thickness, then it modifies the wave equation. I showed you how that works. Well, you know what you're talking about there, deflection of the rod. And then we talked about electromagnetic waves. There we were looking at like the electric field, or the A field, or these electromagnetic fields, wave equation. again, you know what you're talking about. Electric field, you have some understanding about it. He's writing down a wave equation and he doesn't even know what this thing is. But the solutions correspond to something that shows up in the experiment. So there's something right about this. And so it takes a while to figure out what is this psi. And actually, people are still confused about it today. But this book, I think, really helps to establish exactly what is the meaning of this wave function. So the key thing to remember is that the wave function describes the interaction and the existence and the interaction of two entities, the electron and the guiding wave. Right? The evidence of the guiding wave is that there are these resonant modes that can take place, and you get these superposition and interference patterns, just like we see with light, similar things with electrons. So those two entities are somehow described. I want you to pay attention to these things when you're reading for Monday. The inside front cover has a lot of stuff here. We're going to be covering quite a bit that's in here, and this is a nice place for you to see it summarized. Also, when you're reading, each chapter has a summary. At the end of the chapter, there's a summary. Here's chapter 2 summary. As you're reading along, it would be a good thing for you to go back over to the summary because there's going to be like a half page or something that corresponds to what you just read for 3 or 4 pages. There might be something over here. That'll help you to keep from getting lost in the details, keep the bigger picture about what's going on. So on the inside front cover, there's a description up here about what is the wave function. What does it mean? So that's part of your reading for Monday, just to study that. This is crucial. And it comes down to also what is the nature of quantum mechanics itself. So this is a function from which we can extract information about experiments. And the first thing that we will see is that if I take the complex conjugate of psi, multiply it by itself. So this is one thing that we can extract from it. This gives us a probability that should be dependent on time because the wave function depends on time. You take the complex conjugate squared. This is the probability density. And here's how it corresponds to an experiment. If I did a diffraction experiment, I'm sending a beam of electrons through a screen with a hole in it. Talk about the diffraction that happens, even just a single hole. It doesn't have to be multiple slits or anything. Just a single pattern. And I have over here an array of detectors, screen. And I send them through one electron at a time. Each electron shows up as a blip on the screen. Another electron comes through, I get another blip. Another electron comes through, I get another blip. If I accumulate those blips in a histogram, meaning how many show up in a box around at this point in the screen, so I'm going to rotate this. So here's X. The histogram is the probability distribution that we're talking about. How many electrons show up within a narrow range around some value of X. So with that diffraction pattern, we're going to have these kind of fringes like this. The point is that now if I have a rounded value of X and a distance delta X box that Y, P of X, let's make it d of X. It's really small. P of X, d of X is the fraction of the ensemble showing up at that value of X. In the interval between X and X plus dx. inherently a probability. The ensemble consists of one electron at a time, but we take 1 million copies. Each electron is prepared in the same way. We could do it with one experimental setup and do it 1 electron at a time. As long as the experimental conditions are not changing, then we're doing an ensemble. Or I could take 1 million different setups and do 1 electron in each one. So that's the ensemble can be done in parallel, or it can be done in series, as long as the conditions are not changing, and each of these events are independent of each other, right? This setup is not affecting this setup, or at different times. Is there a question? Sorry. Fraction of the ensemble showing up between x and x plus dx. So what you're trying to read? I apologize for my handwriting.
What does it mean by a fraction?
Yeah, okay. Okay, so it's the fraction of the ensemble, right? How many? So if I have 1 million and I get half of them are showing up. So let's do this following ensemble. You got 1 coin each. I give each of you a coin. That's an ensemble of 1 coin. Okay, how many we have? 20. Okay, so the fraction, how many heads? Well, say 7 heads and 13 tails might show up like that. The fraction is then 7 out of 20. That's the probability getting a head. Well, that's not too good, right? It's a small ensemble. That's the problem here. You expect it ought to be the coin is fair. It should be 50-50, but it won't come out that way with just 20 members, 20 samples from the ensemble. So the ensemble, what we mean by ensemble is potentially infinite number of samples, right? They're making more samples. If we do the same experiment now with 1,000, that's still not quite an ensemble. We need a lot more. So if I make 1 million coins, hand them out to 1 million people, everybody does 1 flip, probability is very close. It'll get closer and closer to half, the bigger the ensemble. If you have a small sampling, there's a good chance you're going to be off of 50%, right? In this room, if we did it now, there would be a good chance we might be 3 or 4 heads off, right, from half. The bigger the sample, the tighter the distribution around the average of the expected mean. So this fraction of the ensemble is exactly that. Unlimited number of tries. And so you just do as many as you need to get arbitrarily close to the number that you're looking for. And so this probability is what that means. Probability density is the fraction of the ensemble showing up in that interval. Which means, because it's a fraction, if I integrate over all possible values of x, supposing it goes from minus infinity to plus infinity, then this will add up to 1. Total fraction is 1, right? That's what that says. So a probability is that. There has to be still something going on. I say identically prepared electrons. There's still something going on which is not being controlled. Just like the coin toss. All the coins are the same. They're all fair coins and they're all the same. They're all minted the same way. But each person gets possibly a different result, heads or tails. I could make a coin tosser that would guarantee a heads, right? You could make one. In principle, I haven't done it. I claim I can do it. I think everybody feels he could do that, right? Just make it just right, but it has to be really well controlled. It has to be a good service. Okay, but what we're talking about is, as a practical matter, why we use coins for this kind of thing is because nobody has that kind of control over a coin. You just flip it, and even one person doing it twice can't reproduce the result. You're just not going to do it. You don't have that kind of control. So as a practical matter, there's something that's not being controlled. The same way as something is happening here that's not being controlled, even though I say prepare each electron in the same state, in the same way, something is not being controlled because from one electron to the next, it's showing up in a different place. And that's the puzzle here. Okay. So the wave function is that. It's a manner, it's a thing from which we can extract predictions relating to the experiments, but only for the ensemble. It's only a statistical theory. So quantum mechanics is statistics. And this is the source of the problem for a lot of people. They want to try to apply the statistical theory to individuals. And this is why we're spending so much time talking about probability at the beginning. It's not applicable as a theory about individual members, except perhaps you could say right here, there shouldn't be any electrons shown. The probability is 0, identically 0. That can happen. The solutions to the wave equation, there can be nodes in the solution where there's 0 probability, identically 0, not just small, but 0, for an electron showing up. In that case, you can say there ain't going to be any members of the ensemble there. So that's a statement, that's a blanket statement about even the individual members of the ensemble. There ain't going to be any there. Okay. Otherwise, we're only making statistical statements about ensembles. And that's all we've got. So when you understand this, then a lot of the puzzles relating to quantum mechanics go away. Quantum mechanics, Schrodinger equation is giving us something which will give us a probability density. We're also able to extract other information from this wave function, having to do, for example, with the distribution of speeds of the particle. And so there are other things that we can pull out from this wave function. The first thing we're looking at is this, that psi squared is a probability distribution. This is called the Born rule. And it came after the Schrodinger had published his results. Somebody suggested the significance of this wave function that's coming out of the Schrodinger equation may be this. And the idea here has to do also with the idea relating to light. Again, if you're talking about wave equation and light, the intensity of light goes like the square of the electric field, light wave, electromagnetic wave. So there's a kind of reason for doing this. Kind of makes sense. Also remember, we've got this complex function. And I said the reason for that is because we have both cosine and sine parts independently, but they're compactly put in there. So if I have a real part and an imaginary part, when I multiply by a complex conjugate, I get the sum of the squares of the real part and the imaginary part, right? If I have a complex number in Cartesian form, and its complex conjugate, when I square them, I get x squared plus y squared. I get the sum of the squares of the cosine part and the sine part. Add up like that. So this is a compact way of keeping both of them together. Cosine part and sine part. Probability has both of them together, and the probability is real. Okay, Mr. Ruff.
So the Born rule is when you multiply.
The Born rule says psi star psi is the probability.
And is the incremental reason why probability times the p of x times dx is a fraction of that? Is that covered in the book?
Yes.
Awesome. Okay.
All of this is in the book. Okay, so notice it's a probability density. So let's look at this just so you understand more about what I mean by probability density. It's not a probability, it's probability density. Because when I take p and I multiply by dx, that's a probability. Like over here, px dx is a fraction. So that means that the dimensionality of this thing, what is the dimensionality of X, the length? What's the dimensionality of this? It's dimensionless, doesn't depend on the system of units for length. That means this probability density has to be like 1 over length. All right, that dimensionality of the probability density for one dimension is 1 over length. When we go to 3 dimensions, it'll be 1 over volume. 1 over length. So what does that say about the probability, about the dimensionality of psi? It's like 1 over square length. It's called a probability amplitude. So psi is called a probability amplitude. Related to the probability in that it's complex magnitude squared, is probability density. Okay. All right, so this actually lays out quite a bit of what we're going to be doing. We're going to be looking at solutions to the Schrodinger equation for lots of different situations, and discovering what kind of attributes the solutions have and trying to understand what they mean. Trying to extract from them things that can be measured. But the measurements are always going to be of this kind. Let's leave, collect a bunch of electrons and then make a probability distribution, for example. That's the experiment. Not just one, but for the whole probability. So we're not going to apply it to individual members of the ensemble. And if I have, I don't know, roughly half and half, maybe a little bit less than half girls in the class, half boys. It doesn't mean, so statistically, that's the statement, 40% girls, for example. It doesn't mean individuals are that way, right? Individuals one or the other. It's not like this averaging sort of thing. So we're not going to be doing that with these statistical ensembles. We're always going to be looking at statistical averages. Okay. So one of the things that, well, we're going to talk some more about ensembles. We're going to work our way to solving the Schrodinger equation. But first, we got to have this detour into probabilities. We're going to have some exercises on probabilities so we can understand better the content of the solutions to the Schrodinger equation. Okay, so we said, talking about an ensemble of 1 point. And so which means to make an ensemble, I have to give each person a point. So and I want a lot of samples. So let's do this for everybody in the country. So everybody flips his coin and reports in. I'm going to get tails, I'm going to get heads. So we're going to make a distribution. Let's suppose I put -1 as a tail and +1 as a head. Then I get a bin at -1 and I get a bin at +1. And I get, if I have 300 million samples, I have 150 million tails, really close to 150 million tails, really close to 150 million heads. Not going to be exact, but it's going to be very close. Okay, so half and half, right? 50-50. That's what I mean by ensemble and probability. Okay, 2 points. An ensemble of 2 points. Every person gets 2 points. It's going to flip both points. So each person has 3, or actually 4 possible outcomes, right? Could be 2 tails, a tail followed by a head followed by a tail, or 2 heads. So you can see each one of these is going to be equally likely. We should get a quarter of a fraction, a quarter of the ensemble should correspond to each one of these. Depending on how we say it, if we say, well, you know, how many get 1 of each, then this is 50%. This is half of the ensemble. This is 25, 25. So the histogram would look like this. It'd be 50%. 2 satellites on the side that are add a quarter. The whole thing adds up to 1. Okay. 3 coins. Okay, you get the idea. Got how many possible outcomes? 3 coins. Depending on how you count them, if you distinguish between tail first or head first, how many possible outcomes for 3 coins? Now it's 8. 2. Each coin is 2 possibilities, and there's 3 of them, so 2 cubed. There are 8 possibilities. 8 combinations of 2 things. So tail, 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 head. So write down all the combinations, get 8 possibilities. Each one, if I'm keeping the distinction about the order, each one has equal probability, 1/8. But then I could start grouping them, right? You have a net, and the 3 coins you're going to have. You could have the possibility of 2 tails and a head, or 2 heads and a tail, right? So 3 tails, 2 tails and a head, 1 tail, 2 heads, 3 tails. So now I'm grouping the 8. Okay, so so we know each of these, this is an 8, this is an 8, and these must be the same probability.
You wrote 3 tails twice.
Thank you. These must each be the same probability, and they have to add up to 3/4, right? So it'd be 3/8 and 3/8. That's right. Yeah. Okay, so the reason for this difference here is because I'm not keeping track of the order. What goes into this is tail, tail, head, tail, head, tail, and head, tail, tail. These are all being included. That's why it's 3. See how that works? Okay. So let's do the following experiment. Okay, actually, yeah, let's do the following experiment. Let's give each person about 100 coins. And let's let head mean I take a step to the right. Tail means I take a step to the left. Okay, so now I want to let each person flip 100 coins, take 100 steps, and then I don't care what the sequence is. I just want you to tell me where you end up compared to where you start. Okay, well, if head's a step to the right, tail is a step to the left, then that's going to net displacement from where you started. It's going to be the number of heads minus the number of tails. Right? So your x, so x is equal to the number of heads minus the number of tails. And what we want to find out is the probability, which means everybody reports in where he stopped relative to 0. We make a big histogram. 300 million samples. And it'll look like this. It'll get closer and closer to what's called a Gaussian bell curve. So you're going to work with this, starting off with 1 coin, 2 coins, working up your way to 100 coins. And we could do the same random walk with 1 coin, 2 coins, 3 coins, right? So you're going to get a distribution of coins, heads versus tails. And you're going to study that distribution. It gets closer and closer to what's called a Gaussian. So let's study that a little bit more. Do you have any questions so far? Yes, ma'am.
Okay, that gets closer and closer to a Gaussian because theoretically it gets closer and closer to equal number of tails and heads.
No. No. So there's 2 things to be concerned with here. Let's see. Actually, you're not far off. Actually,
it should be
zero. Say again.
Because at more and more samples, tails should equal heads. It should be 50-50. So you end up where you started theoretically.
Yeah, but what is the probability here? This peak probability. It's not 100%. Just because, yeah. So The important thing there is this width. How does that width change with the number of coins that I've had that I've lost each person? Yeah, in some way. That's right. In some way. So what we're looking at here then, we'll walk up to that. We're getting to that. So your point will be there. So let's hold your point, because what I said was earlier that the get more and more likely to have from your bigger ensemble, the distribution should be peaking. So So there's two different things going on: number of coins and number of samples in the ensemble. That's what we have to be careful. So we have two different things. We don't want to get confused. That's why I'm going so slow with an ensemble of 1 coin, right? And an ensemble of 2 coins. Okay, so let's look at this. When we were looking at, we had 2 coins. We had the possibility of 2 tails, the tail and head in any order, and 2 heads. The probability was 1/4, 1/2, 1/4. For 3 coins, it's like this. And again, ignoring the order, whether it's 2 tails and a head or a head comes first, all of that, grouping all of those together, because we'd end up at the same place, right? All of these guys end up at the same place. So probability 3 out of 8. Okay. So there's the distribution for 2 coins. There's 3 coins, 4 coins. And not worrying about order, how they show up. Any guesses as to how the distribution is going to go? Work it out that fast, or can you see a pattern?
Probably, I want to say 1/2 and all that stuff.
No, it's not going to be 1/2. Yeah. 1/16 here on the end. That's clear, right? It's another power of 2. Go to 1/4, an 1/8, a 16th. Next one's going to be 36. So the fraction out in the wings is getting small. More coins involved, fewer of them are out in the wings, because that would involve a sequence of 4 or 5 or 6 in a row. So I'm like, what's coming in here? Okay, consider this. I'll show you how to get this. I'll show you how to find this. You already know this. If you know the binomial coefficient, you already know this. Work it out with the binomial coefficient. Remember the binomial coefficient. So let's consider algebraically something like heads plus tails squared. That's 2 coins. 2 possibilities, 2 coins. Grouping these together. So this is 1, 2, and 1. That's the binomial. X plus y squared is x squared plus 2xy plus y squared. 1, 2, and 1. How about cubed? X cubed. What's the next one? What's the coefficient of x squared and y squared, and y cubed? Each has a coefficient. 3, 3, 1. Okay. Here. 1, 3, 3, 1. Okay, it's what I'm going to be doing right. Let's see. Here's the 4. Okay, so it's x to the 4 plus what? X cubed y plus what? X squared y squared plus what? X y cubed plus something to y to the 4. You remember how to get these numbers? It's a little like Sherman thing. Pascal's triangle. Right. There it is. Also known as binomial coefficients. The coefficients in a binomial expansion. This is a binomial expanding its product itself for some power. Pascal's triangle. So Okay, you remember how to get the elements? You take this one and this one gives you that. Okay, this one plus this one gives you this one. This one gives you that. So we should have over here 4/16, 6/16, and another 4/16. If we set x and y equal 1/2, which is the probability for each coin toss, then we set x plus y to the 1/2, and each one of these is going to be, this one is 1/2, so the 4th power is 1/16. 4 times the same thing, 6 times the same thing, 4 times the same thing. Okay, so the next one is you just follow Pascal's triangle. Thanks to the next rank down. So the way to get this, the binomial coefficient, big N minus little n factorial. Big N is the power, the number of coins. Little m is the number of heads. And big N minus little m is the number of tails. So this number right here, the coefficient of each one can be written in this fashion. All the entries in Pascal's triangle can be written this way. Factorial of an integer is just multiplying it by itself, subtracting 1 each time. So 4 factorial, for example, is 4 times 3 times 2 times 1, which is 24. So let's do this one. We have 4 factorial at the top. N is 4. Let's look at the 6. So we have n equals 4, n equals 2, and then for n minus n is also equals 2. So we have 4 factorial divided by 2 factorial times 2 factorial. So this is 24 divided by 4 equals 6. That's that number. Okay, so you're going to do a little bit of experimenting, playing around with combinatorics. This is called the binomial distribution. The distribution of coins resulting in coin toss, where I plot on the horizontal axis number of heads minus number of tails. Okay, when you do say 10 coins, it's going to look more and more like a Gaussian. The more coins you toss for each member of the ensemble, the closer that gets to a Gaussian. But what we want to know is how does the max, the peak value, and the width of the distribution, how do those change with the number of coins? That's what we're going to uncover. Another way of saying it is you do the random walk experiment. With 100 steps, each person takes 100 steps. What is the width of the distribution that we're going to get, the histogram? And also, what is the probability that you'll end up where you start? Those two things are going to be of interest studying in quantum mechanics. The probability, peak, height, and width of the distribution. Question? Read everything I wrote. Yeah, flag me down. You can't read something. Okay. That. Have you ever noticed professors, when I say any questions, they wait about 3 seconds. Okay, well, see you on Monday.
Yeah.
Right. I want to give you a chance. I try to not do that. I'm sure I do it, but I try to do that, leave enough time for you to think about what I've been saying, because it takes a while even to figure out what the question is.
So the biggest, so if you make
Still not sure what his question is.
I'm trying to think of the max height max height.
Uh-huh.
That's always going to be.
Well, this would be n factorial over n over 2 factorial times n over 2 factorial. At peak height in the Pascal's triangle, that number, of course, keeps getting bigger and bigger. So it's Cn with n over 2, right? That would be that peak. Factorial divided by n over 2 factorial. And this works only when n is even. Otherwise, we have to figure out, we have, if the number of points is odd, then you can have one more tail or one more head. So that peak height makes a lot of sense if we're talking about even number of points. So that would be that number. You multiply by 1 over 2 to the n. That's going to be the probability of having that. So the probability of being at coming back to where you started from. Does that make sense?
Why did you divide by 2 to the nth power?
Yeah, because each coin toss has a probability of 1/2. They're n points. This just gives you the coefficient out front in the Pascal's triangle, but it doesn't give you the probability of each one. It tells you the relative weighting among all the possibilities. But each one, 1 over 2 to the n.
Flip 2 coins, you have half a probability of being center.
Yes. Right. So for n equals 2 coins. This is squared. N equals 2. So you can see, I mean, the question is, I guess you can keep evaluating this, but what is the probability as n goes to large? Is it going down? Play with this. I'll leave that question.
Yeah, that'd be cool. Yeah,
Less and less chance of ending up where you started. You can do a lot of coin tosses. So this is what we're going to be using to help learn about what we mean by probabilities and averages. Averages.
Does it diverge? Or does it? I mean, I'm sorry. Does it?
I'll let you work on it.
Yeah.
I'll leave that for you to figure out. You're obviously interested, motivated, so I'm going to spend the weekend working on that. You can figure it out. No questions?